Continuing with this section 8.2 notes, we move on to the second page of the notes and to example 2. If in the solution process a contradiction such as 0 equals 2 occurs, the linear system has no solution and is therefore inconsistent. So if you're solving a system of equations in 3 variables and you end up with a contradictory statement like 0 equals 2 when using the addition method, then you can basically stop at that point and conclude that the system has no solution. So I'm not going to say any more about that, and I'm not going to be doing any examples of that type, but just so you're aware, if you do get a contradiction, then you can basically stop and conclude that the system has no solution. It's an inconsistent system. What I want to focus on is another case. The third possibility besides no solution and one solution is infinitely many solutions, or a dependent system. This is something we encountered with the 2-variable case. So if instead the identity 0 equals 0 occurs, and 0 equals 0 is typically what we get when we use the addition method, then there are infinitely many solutions and the system is dependent. And I want to demonstrate how we represent that infinite solution set. So example 2 says solve the linear system, and you see the 3 linear equations in 3 variables x, y, and z. So as we did in example 1, let's label the equations equation 1, 2, and 3. And notice that the y terms in equations 1 and 3 are opposites. So let's take advantage of that and eliminate the y terms in this case. We could eliminate the x terms or the z terms. I would caution you that when you have the possibility of a dependent system, it's best not to eliminate the z terms, because you're going to want to represent your solution in terms of a variable, and in the book they usually solve or express the solution set in terms of z. So I would generally look to eliminate either x or y from equations involving 3 variables to be consistent with the method that's used in the book. You may see, if you look at the textbook, a little bit different method used. It's based on the addition method. It's called Gaussian elimination. And we're not really formally following that. So I would just tell you it's best to eliminate either x or y and to leave z in the mix, so to speak, when you're solving these larger systems of equations. So we're going to choose to eliminate y here, and the first thing we can do is just pair equation 1 and 3 together and just add directly, since the y terms are opposites to begin with. So equation 1 would be x minus y plus z equals 7, and equation 2, it's equation 3, I'll fix that. Alright, so equation 3 is 4x plus y minus 11z equals 18. And then we're going to add terms on both sides of the equations. X plus 4x is 5x. The y terms cancel. Z minus 11z, or z plus negative 11z, is minus 10z. And 7 plus 18 is 25. Now notice there's a common factor of 5 that I can divide out. So let me just go ahead and do that. Dividing by 5, I would get x minus 2z equals 5. Okay, and I'll just stop with that. And what we need to do now is take a different pair of equations and eliminate y again. So let's give me a moment to erase here. Let's pair equation 1 with equation 2 and multiply equation 1 by 2 so that we have negative 2y and positive 2y. So I'm going to multiply equation 1 by 2. 2 times equation 1 would be 2x That would be, again, 2x minus 2y plus 2z equals 14. And then we'll just recopy equation 2. That's 3x plus 2y minus 12z equals 11. All right, and then adding like terms, 2x plus 3x is 5x. The y terms cancel. 2z minus 12z minus 10z, and 14 plus 11 is 25. And you should be thinking, it seems that I've seen this equation before. Indeed, if we divide out 5, we get x minus 2z equals 5. So you see that the two equations that we've obtained are identical. So if we were to pair those two equations together, say taking the first one and just leaving it as it is, x minus 2z equals 5, and then maybe we take the second one just for the sake of using the addition method and multiply by -1, thinking we'll cancel, say, the x terms. Well, of course, you're going to also cancel the z terms, aren't you? So on the left, you're going to get 0, and on the right, you're going to get 0. So we have 0 equals 0. So if the identity 0 equals 0 occurs, then there are infinitely many solutions and the system is dependent. So we're dealing with a dependent system with an infinite number of solutions. And so the question now would be, how do we represent that infinitely large solution set? Well, that's what I'm going to show you next. So we obtain 0 equals 0. How do we represent the solution set of this system of equations? Well, what I'm going to do is take the equation that I obtained from eliminating the y terms from the original, the equations we started with in our system. So we're going to take x minus 2z equals 5. And what I'm going to do is I'm going to solve that for x and write x equals 2z plus 5. Okay, now what I'll do next is replace x. We need to choose one of the three equations in our system, and I believe it will be best to we can use any one of the three. I'll just work with equation 1 since it's the first equation in the list. Let me just write that down again. Equation 1, we have x minus y plus z equals 7. Now what I'm going to do is I'm going to replace x in this equation with what I solved for up above, that is 2z plus 5. So that's going to be substituted in for x here, and then you'll see what I'll do. So we replace x with 2z plus 5 minus y plus z equals 7. What I'm going to do is solve this equation for y. So if I simplify this a little bit, I have 2z plus z, that's 3z, minus y. If I subtract 5 from both sides, I would get positive 2. I'm going to solve this equation for y. So if I subtract 3z from both sides, I obtain minus y equals 2 minus 3z. If I multiply through by -1, I then obtain y equals, let me write it as positive 3z minus 2. So you may wonder what I'm trying to accomplish with all of this. The idea is to express x, y, and z in terms of just one variable. And we're going to use z as that variable. So we expressed x in terms of z, 2z plus 5. We've now done the same with y using one of our three original equations. And by the way, it doesn't matter which equation you use. We could have used equations 2 or 3 to obtain the same expression for y. And then just leaving z as z. And what that gives us is what we would call a general solution. To our system of equations. That solution has the form x, y, z, but we want to represent that in terms of one variable. So we're going to replace x with 2z plus 5. We're going to replace y with 3z minus 2, and we're going to leave z as z. So we express our general solution of the system as 2z plus 5, 3z minus 2, and z. And this is the way it's done in the textbook, and likely the way you're going to see it expressed in the MyMathLab homework exercises as well. So this is why I mentioned earlier that in a case of a dependent system, you want to leave z in the mix. You want to express your general solution in terms of z. So I don't recommend eliminating z at the outset when you're using the addition method. Eliminate either x or y so that you leave z in the mix if there is the possibility that you're going to need to obtain such a general solution of the system of equations. Now, the last thing we might ask is, how does this general solution represent an infinite number of solutions of the system of equations? Well, to see this, what we can do is list what we might call particular solutions. Of the system of equations. And these would be specific numerical ordered triples that satisfy the original system of equations. We can obtain these by choosing really any values we wish for z and substituting them into our general solution. For example, if we choose z equals 0, look at your general solution, that's this right here. If you substitute z equals 0, you're going to get 0 plus 5 is 5, 0 minus 2 is minus 2, and z is 0. So 5, negative 2, 0 should satisfy the original system of equations. That is, it should be a solution of all three of those equations simultaneously. So that's one possible solution, but see, there really are an infinite number of possibilities because I can choose really any real number value for z and obtain a different particular solution. So for example, I might choose to select z equal to 1. If I do that, I would get, using the general solution, 2 plus 5 is 7, 3 minus 2 is 1, and remember z itself is 1. So 7, 1, 1 is another solution of the system. I could choose z equals negative 1. That would give me negative 2 plus 5 is 3. Negative 3 minus 2 is negative 5. And z is negative 1. So you see that this general solution generates an infinitely large solution set of the original system of equations. So this would correspond to two planes in three-dimensional space intersecting, say, in a line rather than in a single point. So this is the dependent system case for a linear system in three variables. We'll continue with example 3 in the next video.